All right, my friends. So let's look at the lateral surface area of this figure. So imagine you have maybe a can of soup and it's, fallen over. That is on purpose. And so we, for whatever reason, need to carefully cut the label. And then imagine that we pull the label off and we want to know how much area would we have. What's the area of the label essentially? Okay, so this length of this label, I hope it makes sense, would be S. And then what would this length be? So I hope it makes sense that that length would be, how far around you would go there. And so that would simply be the circumference there. And so the formula for circumference is 2 pi times the radius. So the lateral surface area of the cylinder, the area of the label here would be, I'm going to use uppercase S for lateral surface area, would be simply 2 pi r times S. There we go. Hopefully that makes sense, my friends. And let's talk about, why was this the warm-up? Well, the goal for this lesson is for you to be able to find the surface area or the area, I should say, of a surface of revolution. So let's show you what we're talking about here. So let's say you have a function of some kind. So function f. And we're looking at, just a part of it, like, what f is doing on a given interval. So let's say from A to B here. And the idea is that you could take this function f just as if it is like a piece of wire in 3D space. So this time we do not, I repeat, we do not have like a bounded region. It's not like the volume problems where you had that region and it was a pretty piece of plastic and then we were revolving it and forming a solid. This time we're going to take function f as if it is just a piece of wire kind of floating out there in 3D space. And we are going to just rotate that wire about some axis of revolution. So for this picture, the axis of revolution would be the x-axis. And then, so instead of a filled in solid, you're going to get just kind of a shell in 3D space. So I hope that makes sense. Let me try to draw this. All right, you're gonna have to be a little forgiving probably of, a lot forgiving maybe of how that looks. Anyway, so the drawing techniques are very similar to what we've done in the past, but what's happening in your head should be fairly different. So this time, make sure you realize that this just represents a shell, a surface out there in 3D space. And then the plan, my friends, is to find the area of it. So like if you were to cover this shell, maybe with I don't know, some beautiful expensive gold leaf covering or something like that, how much of it would you need? So what's the surface area or what's the area of this surface, that is? Okay, so let's think about that. So surface area. Okay, we've definitely, hope it makes sense. We've got an integral at our disposal, and what do integrals do? They add up infinitely many, infinitely small things. So what I'm imagining is, what if I could get infinitely many, what if I could get the formula, I should say, for an infinitely thin little, like, imagine a rubber band. Like, imagine I could cover this thing with infinitely many, infinitely thin rubber bands, and then I would just need to find an expression for the area of one of those infinitely thin rubber bands, and then make an integral, add them all up. So here I'm trying to draw. So I'm trying to draw one of those, infinitely many, or one of the infinitely many, infinitely thin rubber bands there. Okay, so Here we go. Surface area is represented by a big S, which is super fun because if you're like me, your big S's and little S's pretty much look the same. So I'll just try to exaggerate it and make it look like a big S for surface area. And so let's see, let's find the area of one of these little rubber bands, okay? So, so notice that this rubber band right here does look a lot like one of these. It's just that, you know, this S value right here is really, really tiny. Really, really tiny. There we go. And then as a matter of fact, that little S value, you know, you can see that it's kind of on a slant there. And so how on earth would we find that little distance right there, you know? And hopefully it makes sense that, my friends, is just arc length. And so we've already established a formula for that. So take a minute and see if you can recall what formula would make sense for that, okay? So here we go. The surface area, my friends, can be found by simply adding up infinitely many, infinitely thin 2 pi r s's, where the s would be arc length. There we go. So the formula for surface area would be 2 pi is a constant that could get factored out, and then times the integral. Hopefully it makes sense. You'd start adding rubber bands at A and stop adding rubber bands at B. The R here, I'm going to use a word to avoid needing to write down lots of formulas, would simply be the radius, and you're going to stay very connected to your picture to make sure that you have something that makes sense for the radius. And then you're going to multiply that by the appropriate arc length formula. So if you are doing, in this case, I hope it makes sense, you'd be doing a dx integral because you're accumulating rubber bands as you kind of scan the x-axis, then you would make sure that you use the arc length formula that's in terms of x, which would be the square root of 1 plus f prime of x squared dx, like so. There you go. And this is the formula that would make sense if you are rotating a function about a horizontal axis. Okay, I guess I could have put the word here, made it fit a little bit better, whatever. Anyway. Okay, so there we have that. Now let's think for a second, what would make sense to put in for radius if you were revolving around the x-axis? Well, if you look at your picture, you could see that the radius would be the y-coordinate that it takes to get from the x-axis all the way up to the function. And so, and you'd need this to be in terms of x. So in this example, f of x would make sense. But I'm not going to write that because what if we revolve around maybe like the line x equals -5 or something like that? In that case, the radius would be f of x, but then plus an additional 5 units. And so I think we're better off with the word there. Hopefully that makes sense. Okay, before we do the next example, let's talk about what if you're revolving something around a vertical axis. Well, the story is not much different at all. So let's say you have a function, and you figured out how to make it be a function of y, and you're going to revolve it around a vertical axis, like say the x-axis. Then, and let's say you're trying to find, I'll write from C to D this time. Let's say you're trying to find the area of the surface created by revolving F. See. How do I want to do this? Yeah. There we go. So you want to figure out what is the surface area. All right, Here, I will help you get started on this by saying surface area and then big S equals, and then I will butt out and let you do what you're going to do between now and the next video. See if you can figure out the formula on your own, and then check in with me in the next video. We'll see if we get the same thing.